Recording. Here we go. There we go. It's recording now. Okay. Yeah, and that means now we can also start talking about organic chemistry, right? And I'll even go so far as to say we don't have a ton to talk about this week, right? Largely because we've already said it all, at least for substitution and elimination. We've kind of gone through most of what we needed to say, right? The past 2 weeks we've covered SN2, SN1, well, all the differences between those because there's a lot of those differences. And then we also talked about E1, where E1 is primarily in practice, or as far as you'll see it for most of the time going forward, it's going to be you have an alcohol and you put it in really concentrated sulfuric acid and it makes a double bond. And that's really probably going to be the extent of how you see that. SN2 and SN1 will come up certainly more than that, but E1, that's really the practical use of it. And that's like a really common reaction too that you can do, and it's useful. Okay. And that leaves us having to cover E2. Yeah. Which maybe someone chime in and let me know. You've talked about E2 in class. Yes.
I haven't watched the videos yet. I don't know.
Oh. No, not really. Okay. Well, someone was about to unmute. Okay. Well, how about we talk about them for a moment then, and I'll give a brief introduction to E2. And you'll see, well, it's one of these situations where, if you remember when we talked about SN2 and SN1, once we said everything about SN2, there wasn't that much more to say about SN1, right? All of the stuff about nucleophiles and, good leaving groups and everything, it all carried over and applied, right? There were a few kind of differences, right? It's like the different mechanism and like the different benefits of like whatever you're doing SN2 or SN1 on, being primary, secondary, tertiary, all that. But after that, we kind of covered it, right? And so for E2, the thing that we, want to focus on and or the kind of big thing if we're doing E2 and we want to predict a product is where is that product actually going to happen? So an important idea is what types of alkenes are more stable or less stable than others, right? And so how about I even just share my screen and actually show that now? Here we go. I learned that the little box that I make on my own screen is what shows up on the recording. So if I have a really big box, it covers up like half the recording. Anyway, so here we go. Okay, so this is for talking about elimination. Okay, and previously we talked about how the different alkenes are either more or less stable, more or less favorable, right? Given the chance, we're going to form some of them more than others. All right. So when we were doing E1, the stability went in this order, right? So here we had the most stable, and that looked like an alkene which was fully substituted. Okay. And maybe I'll even go a bit more advanced because I have color, right? We have 4 things on each of these. Okay. And then, well, you can only go down from there, right? So here we go. If we have a alkene with 3 substituents, then it looks like this. Okay. From there, we get alkenes with 2 substituents. And I was actually looking into this before the workshop, like the details of it. So these are generally pretty close in energy, so it's actually kind of hard to tell exactly which one is like the most favorable, and it might depend on the compound. But if we were to pick in general, I think we would have something that looks like transalkenes being the best, followed by cisalkenes. Okay. And then also these guys at the bottom, which are called geminal alkenes, for the substituents on the same side. Okay.
Wait, those are the least stable of these three, sort of?
Yeah.
Like similar, but less?
Yeah. So in general, you could probably say that these geminal ones are less stable than, for example, a transalkene. Although I think it'll actually probably depend on what compound you have, and it's like kind of iffy. The difference in energies between these three is like pretty low, and the amount that actually factors into your reaction is probably kind of little. Yeah. Fortunately, when we're doing one of these, it's usually going to be there's usually going to be a clear distinction about which one you should form, because it's very rare that you'll have a situation where it comes down to being one of these three. You know, a choice between let's say multiple of these three, right? It'll usually be like, oh, you can make something with 3 substituents or something with 2 substituents, and in that case, the answer is 3. Okay. And then, well, from there, again, we only go down, and I'll just draw the last one before filling it in. Here we go. The least stable is with nothing. Okay. Chances are you're not taking everything off of your molecule and just making a double bond. But usually things are going to be a little bit more interesting than that. Okay. And then also with E1, remember that we form a carbocation. So we get all of the pleasures and joys that come along with that, especially meaning we lose stereochemistry. I mean, if we have any to start with. And it also means that we can get rearrangements. Okay. And those are kind of the 2 big things to look out for with E1, is that we can get these 2 effects happening. But otherwise, as far as it'll probably concern you from this point on, E1 is really all about taking something like this, and just to give an example that I'm pulling out of thin air because I didn't think of one otherwise, right? So for example, here we go, right? Well, from here, it's going to rearrange. Okay. And as our product at the end, we'll wind up with, well, I guess I should have this, right? And well, if we're picking a product at the end, this is one of those situations where, okay, we can either pull a hydrogen off here, or we can pull one off here. So we can either form a double bond there or there. But if we choose blue, then that double bond is only going to have 2 substituents. If we choose red, it's going to have 3. So, well, we don't go in the blue direction, we go in the red direction. There we go. And there we go. Okay. So that's what we wind up getting. Right. And this is what it'll look like. As far as I could think of, like pretty much all of the time. Okay. And that's what there is to say about E1. Yeah, that's kind of the most of it. I think there are yeah, there might be maybe extra examples, maybe, and from that might maybe sometimes show up that'll be pretty specialized. Like, for example, I remember on the quiz there was something with silver nitrate, and when you put that with a halide, then it'll precipitate out the halide, so it'll leave you with a carbocation. You might imagine that there might be some situation where they say, okay, take that carbocation and now give it a strong base, and that strong base is going to pull off whatever, well, it'll pull off whatever hydrogens are around, and it'll do elimination. Yeah, although if you have a strong base in there, it might already do E2 anyway, and well, that's kind of unlikely that something like that will really happen. Besides the fact that, you've already been quizzed on E1. They don't care about your knowledge of E1 anymore. They just want to know that you can use it to do reactions and syntheses. That's what it'll be important for. But they're not, in general, they try to ask about things like once. And then once you know it, once you're expected to know it, they're not going to just keep asking tricky E1 questions. So yeah, well, there we go. Whoops, that is E1. Okay, and E2, the really key idea here, and well, I guess if you haven't seen this before in class, then the important idea is that, like the difference between SN2 and SN1, it happens in one step. And in order to have this happen in one step, you need to have it be kind of set up in a special way. Okay. So if we have, right, our molecule, and maybe I'll even draw wedges and dashes just to really point out the way it's oriented in space. Okay. Here we go. No, I want my pen. Okay. Here we go. So wedge and dash. And actually, I should have even chosen I should have chosen something else like bromine. Okay. So I drew it this way in particular, and in fact, this is like the most favorable orientation, right? This is like the one time Newman projections will ever come up again. Okay, so we could even draw a Newman projection, and we could say, oh, whoops, I should draw it the way I drew it on the rest of the page. There we go. So I should draw it as a big circle. Well, that's an okay circle, right? And then draw the bromine up, sticking out of the top, right? And then, okay, hydrogen, not that interesting, right?
You just decide like that the left side is the front?
Yes.
Or is it arbitrary or just?
Yep. Yeah, it's arbitrary. So I'm looking at it from this direction, right? And okay, there's a hydrogen down here, and well, these other hydrogens. Okay. And well, what we want is something that's really basic. So we want something that'll pull off a hydrogen. Okay. Okay. So, okay, there's a base, and we'll give it a pair of electrons to work with. Okay. And so the electrons on this base, what happens here, and this happens in one step, what we get is that the electrons on this base come up, take that hydrogen off. Okay. And then the electrons from this hydrogen go up to that carbon-carbon bond, right? Because hydrogen can only have one bond at a time. So if we're making a bond with the base, then those electrons have to go somewhere else. And from there, it's a nice color, purple, here we go. The electrons on this bromine are going to come off, because otherwise this carbon over here would have 5 bonds, right? And we can't do that. So if we want to make a double bond between the 2 carbons, well, then we have to get rid of something else. Okay. And so the reason I drew it even in this Newman projection is because the really important point here, the thing that is essential to doing an E2 reaction, is that these two are opposite from each other. They're, yeah, there we go, like this. Okay. They have to be at 180 degree angle to each other. If you like, this is called anti-periplanar. Okay. That's like the terminology for it. The important idea is that they have to be, one has to be going up and the other one has to be going down, or to the left and to the right, but you know, whatever. Okay. Yeah. So you can imagine, and I'll let me try to come up with this off the top of my head, because so we'll bear with me, but you can imagine a situation like what they gave on the quiz, right? This is like the type of problem that they like to give, where we have a terbutyl group, which kind of locks the conformation, right? Which is, that one's equatorial. So, okay, this is the only ring conformation that we can get. And well, then we say, all right, well, there's going to be a bromine here. Or, you know, let's go for a more interesting leaving group, right? We could pick O-tosyl, right? We'll be a little bit more creative. If you wrote bromine down, whatever, you keep bromine, but, you know, spice things up a little bit. And what you'll see, and what you'll notice here, is that there's no way to pull off a hydrogen that is exactly opposite to this O-tosyl group, right? This is, so in other words, this is not going to go through E2 because we can't get a hydrogen. The only hydrogens around are not at 180 degree angles to it, right? But if we were to give a different example, if we were to just change the position on either of those 2 groups, right? So I'll keep the terbutyl the same, right? And then I say, okay, well, here's an O-tosyl. Well, look, that's a perfectly good hydrogen right there. The ones that are sticking down, right? So I could very well choose these 2, either of these 2 hydrogens. Okay. So that is to say, this will go through E2. Oops. It looks like this. There we go. Okay. And well, if we get that, then our molecule will look like this. in fact, I even should specify we'll get two different molecules because this is a chiral molecule. So should specify that we'll get two different things. Well, I'll write it like this. Okay.
So can we say that when a leaving group is equatorial, then it can't go through E2 then?
Yeah. Yeah, I think that's fair. Yeah, or another way to say that is you can only do E2 on a ring if the leaving group is axial. And there also aren't there are also good hydrogens there, right? So if we were being really ugly and I mean just like this is like such an oddly specific example that I'd be surprised if they would give it to you, but if we were to give like a methyl group here and a methyl group here, right? And then an O-tosyl group. And we actually don't even need the tert-butyl anymore. Right? We could just put the hydrogens here, right? This thing will ring flip. Okay. And let's draw what that looks like. See carefully and one step at a time. So I want this O-tosyl group. Well, I want the hydrogen to be pointing down and the O-tosyl group here. Right. And then from there, these hydrogens point up. Right. And here we go. We have a methyl and a methyl. Okay, well, either way, there are no hydrogens for this to come off with this O-tosyl group. There are no 180 degree oriented hydrogens. So, okay, neither of these can do E2. Yeah. There can be these weird cases where you could do this. Yeah. It's maybe I should mention after the fact, I probably should have used bromine for this case because O-tosyl is also a really big group. It's really bulky. So it probably also will want to be equatorial. But that's besides the point, I guess. Right? We could have used something else. We could have used like bromine or something, or iodine or whatever other small leaving group is your choice. Okay. Yeah. And so this is the key idea. This is really the point. Right. And once we have that, now we can get into the specifics. All right. So in general, if you have, let's say, well, what would be a good example? Okay, well, let's say you have something like this, right? And now we give it a good base. Okay. I've been saying a base. For E2, you want a strong base. Like that's what you're focusing on. Because, well, okay, well, let's look at this one. Okay, how about I explain the base thing first? Okay, let's get rid of that. So let's say that we have a primary halide, right? Bromine. Okay. If we put this bromine in, whatever nucleophile of your choice is, right? It's a good nucleophile. NH3, right? That's a pretty good nucleophile. Okay. Well, this is just going to do SN2. We're not going to get E2 out of this because this is such a good thing to do SN2 on. And this is like a really great nucleophile. So All right, well, that's easy. We're just going to get standard SN2. But we didn't want SN2, right? We wanted to do E2 instead. But that's harder to do now because, well, whatever we put in it is going to be probably a strong nucleophile. Or if we give it any strong nucleophile, it's going to do SN2, not E2. So instead, what we can do is we can start giving things that are bad nucleophiles, but are good bases, right? So we want bad nucleophiles but good bases. All right. So, well, what does that exactly look like? Well, I guess this is the sort of situation where you have to like appeal to the periodic table. And we just remember what makes a bad nucleophile. Okay. So in general, bad nucleophiles were things that were super electronegative, right? Because they don't, no, I think I might have that wrong, right? Well, we if you remember, like as we go lower in the periodic table, those become better nucleophiles because they're more polarizable, right? The atoms are better able to like form positive or negative charges, right? So we want to go up in the periodic table. That is, we want like nitrogen or oxygens, okay? And in general, what you'll do is you'll use oxygen bases, right? That's where this is all going. So in general, things like hydroxide ions, things like methanol, for example, right? If we want to get kind of advanced, we could use like tert-butanol. This is actually a good one, and I'll mention why in a second, right? So we want things like this. These will do good. Yeah, there are some other examples. I think there are some other examples using nitrogen as a base, like nitrogen with a hydrogen pulled off. That could also work, but those will probably be too strong. In general, you wind up using one of something like this, right? You can keep writing out examples. You could write like ethanol, for example. You could write isopropanol is one, and so on. But these are kind of this is the idea. You generally want like a base with an oxygen on it. Okay. Okay. So going back to where we were earlier. So let's say we put sodium hydroxide, super strong base, pretty like okay nucleophile, I guess. Like it's not really good. Okay, and it's got a choice. It can go to either of these two hydrogens, right? This hydroxide, pull off those adjacent hydrogens, and then the bromine will pop off, and we'll make a double bond between the bromine and whichever hydrogen we pulled off. All right, well, we could just choose either of them, right? So if we pull the first one off, we'll get a double bond there. If we pull the second one off, we'll get a double bond there. Okay. Great. Which of these two will it be, though?
Blue.
Yeah, it'll be blue, right? And the reason it'll be blue is because, well, this alkene has 3 substituents. This one up here has 2, right? There we go. Okay. 3 is going to win. It's more stable. It's better. Okay. So this is one of these situations where like we can tell. And
do you mind drawing in the arrows for that reaction?
yeah, actually, let me do it down here. Yeah, of course. Here we go. So, well, we have two different hydrogens that we can work with. So why don't well, I'll draw them on separate places because it'll get too confusing to have multiple different colored arrows and everything. Okay, well, here we go. We have a base that comes in, right? In fact, I'll even be more specific and say it's sodium hydroxide because I specified it in the problem. Here we go. So we have a minus charge, which is going to go and take this hydrogen off. The electrons from this hydrogen are going to go onto this carbon-carbon bond, which is going to push this bromine off. And that means what we get at the end is, well, the double bond forms right away. And then from there, we made H2O and we made bromine minus. Okay. And the alternative here, which we did not go with because it makes a less substituted bond. Actually, okay, let me draw the part that we're focusing on a bit bigger. Okay. The alternative is that we have this OH here, which comes in from the bottom and it pulls that hydrogen off. From there, these electrons go into the bond and the bromine comes off. Right. And same products. Okay. But we said that this was less favorable because the double bond is less substituted. And well, we said that this one was more favorable. Because that double bond is more substituted, and more substituted double bonds are better. Okay. And this line of reasoning, or at least in what we did in this problem, is that so for E2, in general, the more substituted product wins. Product. Okay. In fact, we can give this rule a fancy name if you want, although you've already known it. You've already been doing it all this time. Okay. So if we want, we can call this, there's like a million ways of spelling this. We can call this the Zaitsev rule, right? There's like 50 million ways of spelling Zaitsev, so pick whichever one you like. So we could call this rule, which says that, okay, we get the most substituted product at the end, right? But then this guy called Hoffman came around, and well, Hoffman was a real piece of work, and he said, okay, well, what if I take the same thing that we used earlier, and now I'm not going to use sodium hydroxide because sodium hydroxide is small enough that it can get in here. Okay, so if we have sodium hydroxide, well, let me use my color scheme again. I think I used red for this one. Here we go. Sodium hydroxide is small enough that it can get in there, right? But now if we have this hydrogen over here, if we pick something that's really big and bulky as a base, it won't be able to get that close to that hydrogen. At least more often, it'll go to this hydrogen because, well, this hydrogen is easier to access. It's less sterically hindered, we might say. Okay. So now I'm going to pick one of those really bulky bases that I drew earlier. In particular, tert-butanol. This is the one you're going to see over and over and over again, right? Now, this bulky base will preferentially take that hydrogen that's easier to get, okay? And it's less likely to go this way, right? So if we use tert-butanol, well, then we're going to preferentially make this product instead. Okay. Particularly because of steric hindrance. Okay. Steric effects matter enough that we're going to be getting this product more than the more substituted product. The more substituted product is more favorable. It's more stable, I should say. But in this case, because that base is so bulky, we're going to get the one that's easier to make. Okay. And I'm sure Hoffman didn't name this himself, but we tend to call it the Hoffman product instead. Okay. And the Hoffman product is less substituted. Okay. Let me save this. Whoops. Here we go. Here we go. Okay. And that's what there is about E2. This is like the extent of E2 that we see. Okay. And when we're being practical, we need to think about where do we want our double bond to form, and based on that, which base are we going to use? Okay. For the sake of doing syntheses, you could totally just remember, and nobody will like. My general rule with syntheses is to just pick whichever one reactant will work, and you don't have to be creative, right? Nobody's gonna bother you if you just keep using the same thing over and over again, right? So the reason that I use bromine so often as a leaving group, because, well, it doesn't matter, right? You can keep writing bromine, and they can't say you're wrong. So, in general, you'll use either sodium hydroxide or sodium tert-butoxide, which is this guy over here. Okay. And those are all of the ones that you really need to worry about, at least for writing syntheses. Right. And I guess it's worth mentioning, I've tried to pick nice E2 reactions where it's really obvious that it'll be E2, and it's much more, it's pretty clear whether the product will be Zaitsev, more substituted, or Hoffman, which is less substituted, right? But, well, yeah, you might get some examples where, like, well, they'll give you something like sodium isopropoxide, whatever this is called, right? Something like this, right? It's just a bit less bulky. And then let's see. I don't know, what would be a good example? Well, I guess this is just it, right? Like this is or I don't know, they might give you like this bromine here. Or I don't know. If they put like a bromine here, that would be really nasty because, well, is it SN2? Or is it E2? I don't know. It's kind of hard to tell.
Would it ever do some of both?
Yeah.
Like some products would be SN2 and some E2?
Yeah, exactly. In this case, that would happen. You would get like messy products, so to say, which is that like some of them would be SN2, some of them would be E2, and well, this is, you can get, yeah. So you can get both. So in general, we try to do these reactions when we really know what we're going to get out at the end. And there's like no real ambiguity, right? So for E2, we want accessible hydrogens. We want something that's really basic and not a good nucleophile, right? Except in this case, well, okay, we have easily accessible hydrogens, but this is also primary bromine. That's you could do SN2 on that one really well. And over here, well, this is an okay nucleophile, right? The oxygen sucks, but like it's pretty small. It's kind of small, but it's not that small. So this is like the kind of thing that like could show up in your nightmares, right? Where someone asks you like, "Oh, what happens?" And then you're just like, well, I don't know." And really, nor do they, because this is like an example where multiple things can happen.
Adam, even
Mhm.
though the Zaitsev product was more stable because of the substituted or the more substituted double bond, could you make a case for the Hoffman product also being, I guess, like attractive in the sense that since it takes the more abstractable hydrogen, like it takes less, I don't know, like activation energy to get there, whereas it may not give you the more end stable product?
Yeah, I think so I mean, I guess like there's this whole discussion that could be had about like um whatever that rule is, which I just remembered and I'm blanking on it. The Hammond postulate, right?
Uh-huh.
Which says that it'll be based on like the transition state will be based on whichever is closer in energy. So if we
Right.
have something that's really bulky, then what that does is it changes the transition state energy, right? Because to make the transition state, you have to get that bulky thing next to your molecule, and that's harder to do. So because of that, that means the transition state will be, well, okay, I guess why don't we just actually draw it out? So small, and here's bulky, right? So if we have something that's really bulky, well, that means the transition state is going to be higher. And that means that the whatever we produce at the end is going to be not as determined by the product, right? So I guess that means we'll start down here and then we'll go down here, right? And then if it's small, well, then the transition state is not as big, right? So okay, I guess either way that I drew these, the product is still more favorable, but I guess in this case, maybe you could say there's more influence from the product. Although I don't know how accepted
think,
this argument would be.
yeah, I think like I kind of worded my question weirdly. I guess like what I was trying to get at is how you could get either the Hoffman product and the Zaitsev product, and in certain cases, like maybe the Hoffman product is actually the major one, if that could ever happen, because of the way the molecule is oriented, and like maybe it's not anti-periplanar to begin with, so it's harder to get the Zaitsev.
Yeah, I could see something like, yeah, I see what you're saying. I guess I took the abstract way of getting to it. Yeah, yeah, something like that could happen. And in general, with either Zaitsev or Hoffman reactions, we just tend to write whichever one we want, right? Or whichever one is going to form in greater quantity.
Mm-hmm.
But in both cases, you'll get a mixture. And there could very well be some cases where it's forcing one of the two options.
Okay.
Yeah, I can't think of one off the top of my head, but I imagine that if you have like a constrained ring, so a ring with like a tert-butyl standard example, you could have a situation where that constraining forces either Zaitsev or Hoffman.
Right.
Yeah.
Would
It
something
could
like
be-
heat affect which one you get more?
So
Maybe
it
it's like
might.
the activation energy argument, maybe. Was that
So
not?
I think yeah, so I know that well, so way down the line you'll see another thing that's also a Hoffman elimination, although it's like it happens in a much different way. And in that case you need a lot of heat to be able to do it. So yeah, I think Hoffman elimination probably does take more heat because it involves like doing a harder reaction because you have to get something that's well. Yeah, I guess that bulky thing just is a bad nucleophile all around. So really getting it to do the reaction in the first place is harder. Yeah, this is like going super abstract. This is like one of those things where there's a difference between the product that's thermodynamically more favorable and the one that's kinetically more favorable, right? It's a lot, well, it's a lot more favorable to whatever makes whatever's more substituted, which is the Zaitsev product. But there are cases where like kinetically, it's just way harder to do that. And so we favor whatever's sorry. Yeah, we're kinetically it's much harder to make the Zaitsev products, so we favor instead the thing that's less thermodynamically favorable. Yeah. That is to say, there are definitely like tricky ways of getting which one you want, based on how the molecule is shaped. Yeah. I just don't have any off the top of my head, but yeah. Yeah, cool. How about we? Well, that's like it for elimination. That's kind of all there is to say about. I mean, it still filled an hour of time, but you know, all things considered, it was a lot of just like going through the same stuff. Okay. So, well, why don't we actually look at the why don't we actually start doing problems? And wow, oh my God, we started problems like only an hour in. That's pretty early as far as we've gone. Here we go. Okay. So let me pull. Oops. Here we go. Yeah, I mean, so let's actually start doing them. Okay. And these will also go back through E1 and E, or sorry, they also will go back through SN1 and SN2 because, well, they are also pretty essential, and you will be using them like forever and ever. And besides the fact that SN1 and SN2 are pretty like closely coupled to E1 and E2, as we saw up here, right? You can get, we would say you can get competition between the two sets of reactions. So okay, well we were just writing some stuff about SN, or we were just writing some stuff about like energy diagrams, right? So this question asks about energy profiles for SN1 and SN2. So this is like for SN1 and for SN2. Well, here's energy and here's the reaction coordinate. I guess people write RXN for reaction. Sure, why not? Right, and here's energy. Well, okay, cool. So for SN2, this one's not bad, right? Because we know that for SN2, we start with, well, we start with both things, right? So here we go. We have X plus something in a leaving group, right? Oh my God, look, none of these are even chemicals, right? Yeah, so there we go, right? And then we have a transition state, right? And then we get our final product. And that's it, Right? So here we go. We have the starting state. We have the transition state. We have the ending. Okay. And here I drew it to be exothermic, but nobody said it has to be. So that's it. Right. And this is the transition state. Okay. So with SN1, okay, we start here, we end here. Cool, right? So what is the difference? What's the difference in this middle region?
You actually have an intermediate on its own as its own rate determining step. So that'll be the first kind of peak with the highest energy. And then you should have a following peak where it's the carbocation is actually attacked, and you could have a various number depending on rearrangements and such.
Yeah, right. I wasn't even thinking about rearrangements, but yeah, there you can have plenty more in the middle, right? So the important point is there are two peaks here, right? And what that really tells us is there has to be a little dip in the middle, like a little well. Okay. Yeah, I don't know however you might like to think about it, but the way that I really think about it is literally like molecules are pooling up in this little well. Okay, right? And then they overflow and they go down. Okay, that's like a little cartoon way of thinking about it if you like, but obviously that's not the official way, right? That's not like the scientific way, but it's the way that I like to think about it, right? So if you have this little dip, molecules will pool up there, right? So this is the carbocation, right? And then this is what you start with, which is reactants, and this is products, right? And then you have one transition state and a second transition state. Okay. Which is kind of weird to think about because we never really talk about these in E1. But the first transition state, if we want, well, it'll look something like this, right? If you have a carbon and then and then something there, the first transition state is literally when this thing is kind of off, kind of on, but it's kind of off. It's like in the middle. It's between the two, right? And then from there, well, then we get our carbocation, right? And for the second transition state, it's the same thing, right? Maybe I should have used L for leaving group instead. I guess I'll go back and change that. Yeah, and also get rid of this. Here we go. I don't know why my window for my pen turns. Oh, there we go. Okay, I can fix it now. Don't know what that was about. Okay. Right. So this is the first transition state, and then the second transition state is when, oh well, whatever we're adding is kind of on, but it's kind of off, right? And then we make our final bond, right? These two transition states aren't interesting, right? There's like, this is not like this is not the part that people are interested in. We care way more about these things. That is what we start with, what the intermediates are, and what the products are. The transition states aren't usually that informative. Okay. Sound good. Let me get what's next. There we go. Okay. This is a ranking question, which, well, I don't know about you, but these are like in my opinion, like the worst questions in organic chemistry. Like these are these questions, like, they're no fun. Nobody likes doing them, right? But they come up, so, well, I guess we might as well practice them, right? So that we were able to do them well when the time comes. Yeah. So okay, well, let's do that then. They don't go away, I promise you. So here we go. Let's look at this. So we want to rank them in order of increasing nucleophilicity. So why don't we start with worst nucleophile to the best. Okay. And well, let me draw a little periodic table for us for reference. Right. And well, here we go. Right. So here is nitrogen, here's oxygen, and here's sulfur, right? And then, oh, I don't know, there's some other stuff going in each of these directions, but I don't remember that much. So here we go. Okay. That being said, any suggestions on which of these is either worst or best? Does any of them really stand out as being a good choice or a bad choice?
Would the sulfur one be the better, well, it would be the best one because it's the most polarizable?
Yeah, exactly. I agree with you. So, yeah, we could say, and by the way, these sodiums don't, I mean, they don't, that doesn't mean anything, right? Like the fact that it's a sodium is, I mean, we just care about the anion, the part that we're actually going to be using as a nucleophile, right? Sodium, we might say, is just a counter ion, meaning that, well, it's just there to make sure that charge is balanced, right? You just need it because otherwise you would just have a bunch of minus charges floating around alone, and that's not okay. But yeah, this is the most polarizable.
Is that because of like the electronegativity of S? Sulfur?
So it actually comes down to the fact that S is larger. So like it really is just down to the fact that, like, if you have an oxygen, right, and we draw a really bad electron schematic and we have a sulfur, well, this sulfur has way more room to build up a bunch of like minus charges. So for example, we can build up all this minus charge and we can move all the plus charge over to here. That's not exactly what the case is, because really there are no plus charges floating around the sulfur atom, right? It's just electrons. So really all the electrons just tend to move this way. And this minus charge doesn't really happen. This is not like a real thing. But this happens because it's larger. With oxygen, we get like less of that happening. Yeah. Although you actually have a point. The sulfur it's lower in the periodic table too. So it's less electronegative as well. And that also means it's a better nucleophile. Yeah. I tried to mention this earlier, but I got caught up on my own words. Things that are more electronegative tend to be worse because they want to hang on to their electrons and they're not willing to give them up to something else. So fluorine, for example, is consistently one of the worst things to react with because, well, it's not going to give up its electrons. Like it will do everything it can to avoid giving those up. So, yep, here we go. Okay. Most polarizable. Less electronegative. Okay. Well, from there, what is next?
like going off the electronegative, so like N is better than O.
Yeah. So I would say so. Okay. Yeah. So I think oops. Yeah. So this NH2 is going to be better. Right. Okay. And now we're left down to the two oxygen ones. And so here we go. We have an O-methyl and an O-acetate, which we're comparing this with this guy here. Okay. All right. And now any ideas between the two of these two?
Would this have to be with like sterics? The fact that like the acetate group is bigger, so it might be harder to like attack a carbon.
Okay. Yeah. So that's okay. So that's one thing to think about. So we already have sterics, and this acetate will be slightly larger. Yeah. It's worth saying. Acetates are still pretty. The acetate is like a small group. So it's not going to be substantially larger than this methyl, but okay.
I was thinking maybe you could compare like how acidic each of their conjugate acids are. So like I think methanol is worse as a conjugate acid, so the the acetate group maybe is more nucleophilic.
Okay. Mm. So yeah, maybe. Yeah, it's so you could go with that like line of reasoning. It's hard to say exactly how acid base wants to how acid base like corresponds with nucleophilicity, right? Because we could have some acids and bases that are really good nucleophiles, or we could have some things that are really good bases but weak nucleophiles, and the other way around. Yeah. So someone says here, so we have two oxygens, then they're more more polarizable. It might be the case. Yeah, although I think what it so so you could have it really polarized with these two oxygens, and even more so, right? We could do resonance, and we can say like, okay, if we have like something with a leaving group here, not enough space. Here we go. If we have something with like a leaving group here, right? And well, then we'd be able to move this minus charge forward, right? Although in terms of each of the individual oxygens, I mean, these two oxygens are sp2 hybridized, right? And that means their electrons are closer into the center. So that might actually make them less polarizable. Okay. Yeah. So this is kind of one of those situations, and if you remember from acids and bases, how polarizability like affects acids and bases, or just like reactivity. What you'll remember is that having something be so if you remember, like having something be polarized, more polarized means that it's less likely to give up its electrons. So in this case, well, even though you can move electrons by resonance, so sp2 hybridization, so it makes the acetate less nucleophilic. Okay. So it
Oh.
wind, yeah.
I just wanted to say, so could you use this like backwards ranking of like nucleophilicity to like determine which one's better for E2 reactions?
Yeah, you can. Yeah, so at least that is the things that are worse nucleophiles, they'd be less likely to have SN2 competing, right? But well, if we fill in the rest of our ranking now, the thing is like this is like not a good base though, right? This is a pretty stable, well, it's the conjugate base of acetic acid, but it's pretty stable, right? This is like happy on its own as it is. So that wouldn't make it really good for E2 because it's not a good base either, right? It sucks as a nucleophile and it sucks as a base too. It's not really good at anything. Yeah, so this is like a case where you can use it to tell between well, where it's not really good at either. But well, okay, this one here, O-methyl, this is great for E2, not that great for SN2, right? In fact, we just showed it's a pretty bad nucleophile, at least when you compare it to all this other stuff. So this would be good for E2, right? And then this is over here good for SN2. Yeah. So with all of this, there's like it like things being good nucleophiles and bases tend to come together, but they're still different ideas. Things being good nucleophiles and good bases. Like you can have weak nucleophiles and weak bases, good nucleophiles but weak bases, weak nucleophiles but good bases, and good nucleophiles that are also good bases, right? You can have all four possible things. In fact, why don't we even, and let's see if I pull this off because again, I did not plan. At least I did not plan to include this, right? So like, let's say we could do right? We can have good, bad nucleophiles, and we can have good and bad bases. And we could, let's say, draw examples for each, right? So what's like a good nucleophile and a good base? Well, any thoughts?
Would the good base bad nucleophile be like the would it be like alcohols almost?
Good base, but kind of bad nucleophiles. Yeah. So like
ROH stuff?
for example, like this, right? This is a good base, but it really sucks as a nucleophile. It's really bad. And for example, something that's a good base and a good nucleophile could be like hydroxide, right? It really does both. Okay. And well, we just said what would be bad at both because we just did it in this example, right? But what would be a bad base but a really good nucleophile?
Like iodine?
Yeah, sure. Yeah, right.
Iodine.
Yeah, anything that's not really a base. I mean, there we talked about plenty of other ones. Iodine, yeah, this is like probably the good example, right? If we wanted to keep with the theme of whatever else we had here, right, we could do something like you know, so something with a sulfur, right? And whatever other group, right? That's a good example. Sulfur is fairly acidic, as a pK of like 8 or something along those lines. But I might be mixing that up with another number. So that's like, it's not a good base. It's kind of acidic, in fact. But it's a really, really great nucleophile. But you know, whatever. Iodine completely covers everything we needed, right? So this is just yeah, go
I
ahead.
had a question about like still about the O acetate with like the OME. I'm still a little confused about why like the one with the methyl would be a better nucleophile. Like would it be like, would the sole or like the biggest reason be because like it's sp2 hybridized, so like it's less likely to react as a nucleophile, whereas like for example if you had like an ether or something, like does the other oxygen group, besides the fact like does another oxygen group, would that also have a similar effect, or is it just mainly because it was like sp2 hybridized that it was like a worse nucleophile?
I think it's really because of sp2 hybridization. I guess and I guess I didn't mention this earlier, and I don't know to what extent this does play a factor, but with nucleophiles, their charge is also a factor, and in acetate, the charge is really distributed between two oxygens. So, like for example, with this O-methyl, so all of the negative charge is on the oxygen and it can't go anywhere else, right? Whereas with the acetate, it's split between two oxygens, and you can push it to more to one than to the other, right? It's polarizable in that sense, which is that you can give more of the electrons to one of the oxygens than the other one, but it doesn't, it's still not all the way, right? That charge is still going to be split between those two oxygens. So either way, you're still going to get a little bit less than a full minus charge on one of the two. So it's split. Yeah. So this is like, I guess with all of these effects kind of add up. So there's the charge being split on the acetate. You have the sp2 hybridization, which doesn't like help. It makes it harder to give up those electrons. Although we normally don't talk about hybridization so much when it comes to nucleophiles, but I mean, that also comes up. So, and there's the minor steric argument, right? Which will kind of make it a little bit worse. Yeah. This is like kind of one of those problems which I know in my experience, I like saw once and then just remembered that acetates are bad nucleophiles. like if you look at this problem, not that this is like, I mean, it's good that we went through and we worked out the whole thing, but like, you know, nucleophilicity typically in practice, at least, the way that I've always used it is I've just kind of remembered what that table has, right? What is a good nucleophile? What's an okay one? What's a bad one? And that table would completely cover us, right? This was one of our really good nucleophiles. NH2 was also a very good one, and then O-methyl is like kind of okay, and then this acetate is a bad nucleophile, and then like it was classified on that table, and it would work. Although, you know, deferring to memory is not always the best option, so working it out is good too. Yeah. So anyway, yeah, to answer the question, so I think it's kind of the combination of these, the charge and the hybridization, and that's what does it. Yeah. Cool. Let me just save this. And then open up. Okay, here we go. Here's the next problem. Okay. I'm not going to copy all the instructions, but the point was just, here's a bunch of compounds, show how you would synthesize them with, I think it was SN1 or SN2. So that's what we're worried about. Yeah, there are instructions about it, but well, whatever. Yeah, here we go. Okay, sorry, just opening up my windows. Okay, cool. So this is what we have. Okay, well, and the question asks, well, we want to, let's say we want to make this compound over here. And we want to do it by the exact wording. The problem is the nucleophilic displacement of alkyl halides and provide appropriate reaction conditions. Okay. So I'm going to use this double arrow here. Okay. And this is called retrosynthetic. This is a retrosynthetic arrow, meaning that we're going backwards. Okay. And now that you're, well, you've seen your first synthesis problems, this is when retrosynthetic analysis starts to become useful, because it's saying, okay, I have a product, right? And maybe I have something that I started with, and I have no idea how to get back there, or how to go from what I started with to what I ended with. What we can do instead is say, okay, I know what I'm ending with, or what I want to end with. So I could just look at what's on there, and I could work my way backwards. Okay, that's all that it's saying. So the idea here is just, we have this OH group here. Well, how do we know how to attach an OH group?
Is it SN2?
Yeah, so we could do an SN2. It'll be a kind of crappy one. This is a bad problem to start with, because it's not like going to be good. But let's say, yeah, sure, we could have something with like, okay, whatever, bromine. It doesn't matter what it was, right? And I drew the stereochemistry inverted because, well, if we're doing SN2 and we want this exact product, then we have to be able to we have to invert the stereochemistry, right? And so if we were to go forward, well, if we want to do it with SN2, then here we go. Okay, use sodium hydroxide. The question also asks for reaction conditions, and I guess it's a good habit to get into doing that. So what's somebody's favorite SN2 solvent?
AMSO, DM. Yeah, that one.
Sure. Yep, sounds good. It's a good one.
You not like do SN1 with water because they like said it's that one enantiomer like that the OH is on a wedge.
So yeah, you're right. If we were to do SN1, we would lose stereochemistry. Yeah. Yeah, so that I guess that is one way we know that it has to be SN2 and it can't be SN1. But I mean, it is really worth saying, like, this this reaction with the sodium hydroxide, this is an excellent base, right? It's really good, it's super basic. So you're gonna get a mix of E2 as well. So you get the E2 product as well. And if we're doing this in just one step, or in other words, if we're just doing this with the reactions that we've learned so far in the class, this is the only way to do it.
So when you're like, they show you only one stereochemistry, you assume that you don't get both.
Yeah.
So like that it's not like some, okay.
Yeah.
Okay, so they just like not put the wedge on it? Would they just do a normal line if they didn't care about stereochemistry at the end?
Yes.
And then it could be SN1.
Yeah. Yeah. Also, if they're looking for stereochemistry, they'll usually like really signal that by saying optically pure. For the product especially. But in this case, yeah, I mean they did show us the wedge, so we should just assume it's optically pure. Yeah, if they specify, then you can assume that.
Did we talk about like the stereochemistry for eliminations?
So with E2, well, so we're making a double bond, right? So so we either get cis or trans isomers, right? Or E or Z isomers, depending on whatever convention you call them by. But that's like, this is the importance of having something be anti-periplanar. So for example, if we take like this molecule here, this bromine molecule here, right? This is chiral, and this is like a really bad, maybe I'll make it a more obvious chiral example because this kind of sucks. Right. There we go. That's nice and chiral. So if we take something like this and, well, we wanted to do E2, well, then there's a hydrogen over here. Okay. And so we need them to be anti-periplanar. So this is kind of the situation where we want to draw it out. We want to change how we draw this so that we have something like this. And then from there, this will affect the stereochemistry, right? Because well, if we put it in base, strong base and heat, well, then it's going to take off this hydrogen, goes up here and then up to here. And then this whole thing goes from like being this big 3D structure, and then it flattens, right? It gets squished. So, well, in this case, we wind up getting methyl, then OH over here. And then over on this bond, we could have twisted any way we wanted. So we could have it, the methyl over here, or we could get the methyl down at the bottom in this case. I guess it'll just matter. So yeah, actually in this case we get both products. And well, the reason for that is because we have these two hydrogens, right? It will matter, I guess, if we have like something even uglier, right? So if we have like another methyl over here, and now this is getting like to be a a complicated example, but we could redraw it, and let me use different arrows just for the sake of it, right? So now, okay, let me even make it longer, right? So it's now we have two chiral centers, I guess. Okay. See, and this molecule is now getting ugly, right? Because to do stereochemistry, we got to pick really specific stuff. So now we can have our case where, like, we have this bromine, and we can rotate, and you could do all the mental gymnastics, or really you could build a modeling kit because this is getting like unwieldy. But in this case now, and well, the whole right-hand side is the same as what we had earlier. So now we could take this hydrogen off. This goes onto here, and this moves, the bromine pops off, right? And this whole thing flattens, which means that the only product that we would get in a case like this is something that looks like this. Okay. So in this case, we would just get one product, right? But otherwise, we had multiple hydrogens to remove, so so we get both E and Z. So it comes down to depending on what molecule you're working with.
So like whether it could rotate or not.
Yeah. Well, I guess could you clarify what you mean, just so I talk about the right thing?
Like how, like in the first example, you said there was two hydrogens. That's why you could rotate it.
Yeah. So it's well, we could have either the methyl coming out like this and the hydrogen going into the page like that, or it could be like the hydrogen coming out and the methyl going in, right? And the reason is because we could just take this, we could take this bond up here, or this whole thing, this whole carbon up here, and we could just rotate it, right? So we could just say, okay, well, let's swap this up here, this down here, this over here. Because it's still a single one.
Is it like rotation around the single bond that differentiates it from the other one? Or is it like the fact that you have more than one hydrogen you could remove, so you have a choice?
So you have the choice. So in either of these cases, you could rotate around this single bond. So you could always just rotate like this, right? Which is what causes these to cycle. But well, yeah, and you could do it here too, right?
But is it too like bulky? Is that why I think they mess with each other? If you were to do the diagram thingy.
So in this bottom case, the only way you can get these to react is you need this hydrogen and the bromine to be opposite.
Oh, for the 180 thing.
Yeah, right. And so the only way that this one can react, there we go. So it can only react when it's antiperiplanar. Okay. And this is the only possible way for it to be anti-periplanar. There's no other way to arrange it. Right? Whereas with this one, you have two hydrogens. So you could just rotate them and make it anti-periplanar. Right? So, well, you could rotate around that single bond. You could switch which hydrogen you're reacting with. Yeah. So, yeah, you can make sometimes both E and Z isomers, or both cis and trans, if you have multiple hydrogens that you can work with. If there's only one hydrogen there, though, that you can work with, then you have to think more carefully about it. And then you might just get one of the two. And what it always comes down to is you have this big molecule and you just squish it, right? It flattens into one space, one plane, we might say.
Okay, thank you. It was kind of a detour, but yeah, we can go back.
Yeah. No, that's okay. I mean, this is the important stuff.
Question. Oh, going back to the example. So how do we know that the hydroxide reacts with a hydrogen on the carbon skeleton and not in the OH group? Is it because of pK values?
Yeah. So do you mean like, why didn't we just do an acid-base reaction with this?
Yeah.
Yeah. So, yeah, it could have. I kind of glossed over that, but if we'd have to put in enough sodium hydroxide for that to happen, we'd have to add a whole bunch. Yeah. In fact, this example can get kind of messy because, well, oh, look, I'm at the bottom. You know, you're at like you're getting up to the point where you can say like, okay, if I have something like this, right, and then I treat it with like, you know, whatever's a really, really good base, right? Sodium amide. No, let me just use sodium hydroxide again. Right? Then we can get something like this. And well, we could just do SN2, right? Inside of the molecule itself. I mean, no reason we can't, right? This is actually super useful. This right here, this like little stupid compound that looks like it's under a lot of stress, right? This is super important. You will get to this in a few weeks, and this is like your best friend, or I mean, really your worst enemy, because it's complicated. But this thing is called an epoxide, which is a little triangle with an O, and there's a lot you could do with it. Right. So that is to say, this example is kind of flawed because, well, there's some more stuff that you can do, but you know, if this OH was anything else, yeah. Okay. Cool. Well, let's just run through the rest of this problem, and then we'll talk about the next few next week, or you know, you can work on them at home or something, and we'll go over them. Okay. All right, so we want to form this ring closure, which is good because that's what I had just mentioned, right? We could do ring closures with SN2. So let's say that we want to start with, and this is one of these times where like it is essential to count hydrogens. So let's say we want to start with something that has, oops, I don't want color anymore. So we wanted, let's see, 1, 2, 3, 4, 5 carbons, right? And then, oh, I drew the S in, but maybe I shouldn't have done that yet, right? And then if we look at our structure, we can tell that we need something on carbon 5 and we need something on carbon 1, which I already drew the bond for. Okay. So we need something here and we need something here. Okay. So one of them will be a leaving group and one of them will be an SH, for example. Okay. Any ideas where each should go? Let's just say it's a bromine for a leaving group. Any ideas on which should be the bromine and which should be the sulfur?
Maybe the bromine should be on the left-hand side and the sulfur can be on the right-hand side so it can close the ring with its lone pair.
Yeah. Yeah, so if we have the sulfur here, well then we can go here and then we can get SN2, right? This is a nice reaction. In fact, this is a pretty favorable reaction. This will happen pretty easily, all right? And so we could start with this, and then going forward, we'll probably want to pull that hydrogen off so we can give it like a, we can give it some sort of base, right? If we really want, we could give it, I think you saw this one showed up on your quiz, so we can give it potassium carbonate, which is just a kind of weak base, and like whenever you get a hydrogen that comes off, this will just take it out. So it'll bubble off, it'll form carbon dioxide, and well, that's like irreversible, so that's pretty nice, right? It's pretty easy. This is one way to do it, right? And then this reaction is SN2, so pick your favorite SN2 solvent. Why not acetone? Good one.
Do people like draw acetone instead of writing the name mostly?
No, you could write acetone. Yeah, that's perfectly fine. Yep. Yeah, so this is a good way to do it. In particular, the point is we could not have put the bromine on this tertiary carbon. Okay. The bromine can't go here because then it would be like SN1. And well, this is going to work all the time, like 100% of the time. There's nothing that would go wrong in this reaction that we've set up. If we set up SN1, well, we need to do it in a certain solvent, but that solvent could also react with it, right? Also, SN1's in equilibrium, so we like lose some of our product, and SN1's not as nice. Okay. Cool. There's another one. All right, so if we want to go backwards from this one, well, this is pretty ugly because we've attached an acetate, except we just said earlier that acetate is a weak nucleophile. So I'm not a huge fan of this problem either because, we're going to try to avoid doing things with weak nucleophiles, and there are much better ways of making this structure that don't involve SN1 or SN2. But
is the product optically pure? Because the T, is it chiral because of the tert butyl group?
So it is pure, but, and you'll hate me for saying it, this compound is meso. Because if we looked at it like, well, I mean, we could draw it in a really ugly way and say, oh, like here, right? And we could draw this mirror symmetry, right? If I drew it like standing upright, or I drew this carboxyl or this acetate like standing upright, for example. This product is meso, so
like, I guess the one thing I'm still not sure of, like, how do we know to look at it like in the chair conformation or like in the flat like hexagon looking conformation?
Yeah, well, so you were right. This is pure in the sense that it's just this isomer. And if it was supposed to be the other one too, they would draw it as, oh, oops, drew this wrong. Right. So if it was supposed to be the other one, they would draw it as being equatorial. Right. So they would draw it this way instead. When they draw it flat, right, you'll only be able to tell based on if they draw wedges or dashes, right? And to go from this to the chair conformation, well, you have to pick, let's say just pick one, right? So let's pick this acetate, and I'm going to draw it over here, right? Going up, because here it says it's going up. So the way that I drew my chair, it's going up too. Okay. Even if I drew my chair the other way, right? So if I drew my chair going in the other direction, and I picked one of these carbons to be my acetate, this one, right? Then I would go and you would count your carbons. So 1, 2, 3, and 4, right? So this is 1, 2, 3, and then 4. And over here, 1, 2, 3, and 4, just to make sure we know exactly where the other one lands up, right? And here, this tert-butyl is also going up. So on here, I pick the position that's pointing up. On this one, I pick the position that's pointing up.
So I guess I was just more wondering, since like if we know it's like, I guess like I thought it was chiral, so you had to do SN2 on it. Like, would meso mean you have to do SN2? Like, and like SN1 isn't an option any, like regardless of any other facts.
Yeah. Yes. So I guess I threw in the fact that it's meso, although that might have done more harm than it did good. This is this is optic, or it is pure, right? This is like it is pure, so we have to do SN2 because otherwise we would get that additional thing, which I guess would also be meso, but
Where are the chiral centers though? Because isn't it like symmetric?
actually,
Like isn't it like the same? It's not like the T-butyl is like shifted.
Yeah, you've got a good point.
Wait, I was just confused because I thought like the T-butyl group would make the conformation so favorable to be in the like the equatorial that I wouldn't want to like flip to the axial conformation. So like because of that like energy difference, it would be like stuck in like that conformation only.
Yeah, you're right. Yeah, so it will be stuck in this conformation here. So I guess I can get rid of this pure part because, well, yeah. Yeah, so it won't be. But my point was just like, if you want to go from drawing this to the chair conformation, right, you can draw it this way. Because, like, even though you won't see this ever showing up, right? We could use it if we pick one way to draw the chair conformation. And then if we wind up finding like, oh, well, shoot, I drew my tert-butyl being axial, then you could just do a ring flip from it and get what the correct thing is, what it should look like.
So like T-butyl will never like actually be axial because it's too big.
Yeah.
So you always have the ring flip. I guess unless there's something that interferes more on the other side.
Yeah. Yeah. So yeah, I guess the idea, yeah, if you want to draw from like the flat drawing and you want to go to the chair conformation drawing, you could pick what you could draw it, like just draw a chair and then fill in the substituents based on what's here. And then if you find like, oh, look, this, I went to this one first and I drew it wrong. Well, then you could just do the ring flip, right? And then you'll get the right, the better confirmation. Yeah, that's you could do it. Okay, and then I guess just to wrap up this one problem, because we're eating up time. Here we go. So yeah, so we could, it's really bad, but yeah, we could do this by SN2, right? If we have, let's say, if we have this chair and it's locked in this position and we can't really do anything about it, well, we're going to want a hydrogen up here and we're going to want the bromine or whatever leaving group to be down at the bottom, right? Because we want to kick this bromine off and we want to kick this hydrogen down, right? So in that case, we'll need to do it by SN2 because we want this to stay up at the top, right? And so we can do SN2 like this. Okay. Cool. We've eaten up our time and we've run out. So we'll finish up these problems. We could do them next time and finish working on them. They're good problems anyway, and they'll be useful for like review. So that'll be good for us. In the meantime, here we go. Stop share.